See, centrifugation is not really new to you, right? We know that centrifugation is a mechanical technique where centrifugal force is applied. Why we need this? See, any macromolecule, maybe carbohydrate, proteins, or even complete entire cell also, you want to separate out. So it is going to get settled on account of its size, molecular mass, and the force acting on it, right? So gravitational force is always acting, and it helps to settle the particles or materials in a given liquid solution, sample solution, whatever you have as a suspension of cells, for example, right? So with the help of gravitational force, the denser particles, denser or cells, you can say, they will start settling based on the properties like mass and density measure. All right. So if you just keep muddy water uh, and hold it in a tube for longer time, what you will see is some of the particles they get settled and water slowly becomes comparatively clearer, but some fine particles they will not settle at all. So if you want to completely remove all that debris from water, solubilized particles you cannot separate by centrifugation, but suspended particles of smaller size also you can separate, which cannot be which won't be settling by gravitational force, gravitational sedimentation. We can apply external force, and that is what we call it as centrifugal force, right? So it is applied to separate the components in a mixture based on size and or density. Only bigger size but they are less dense, then they won't be heavy as such, right? So bigger size and more density, then they will be more heavier. So size and density are the two criteria which are going to be important. And now, when it comes to the field of application of biochemistry, cellular and molecular biology, medicine, pharmacy, chemistry, everywhere you need applications of centrifuge, and you have different types of centrifuges which are going to be working based on what kind of centrifugal force it can generate and what speed it can attain. So that is one type of centrifuge which is just meant for separation or of the particles or preparation of a particular fragment of cell or for a preparation of particular type of macromolecule from rest of the cell suspension or cell lysate, so on and so forth, right? For separation you can use it. At the same time you have analytical centrifuges which are going to not only separate the molecule but also are going to analyze its characteristics, how that we have to learn. Now, when you talk about separation, you talk about centrifugal force, you talk about the size and density of the particle, and another important is the duration or time for which centrifugation is to be run that will allow the sedimentation of a particle. Right? So, these are the few key points when you talk about a centrifugation process. Now, when you are talking about particles in a suspension, then the effect of centrifugal fold you can imagine. What is centrifugal fold? There are two types, centripetal and centrifugal. Fugal is going away from the center and centripetal is towards the center. We want the force which is working away from the center, that is centrifugal fold. So force. So the particles will be moving towards outward, then they slide down the centrifugal tube and they will settle at the base. That is how it works. Now, when we are talking about the centrifugation as such, rotation axis, specific revolutions per minute, and the time. These are the three factors which are very important. So, we are talking about the properties of the material which is under sedimentation. उसमें क्या क्या आ रहा है? The size, the density, right? And second part is that of machine. So in that case, what is the centrifugal force or centrifugal field that is applied? What is the time given? And what is the uh, distance of the particle from axis of rotation. These are the three important things. Closer the particle from the center of axis of the centrifugal machine, or whether it is away from it. If it is away very shortly, it will be reaching to the outer wall of the tube, and it will slide down and it will settle. So these three are the important components from the machine point of view, get a good separation or good sedimentation. So उसमें क्या क्या है, एक है the centrifugal field that you are applying, दूसरा है time of application given, and third is distance from the rotation axis. Now all these things give you that this particle will get separated when revolutions per minute is so many thousands for so many time, so many minutes. That is how we express, right? Revolution per minute. So that is the speed of the centrifuge. That is another factor. Now, how do we count that? How many times the centrifuge is rotating in a given unit time? Say 1 minute. So 10,000 times, 5,000 times, 2,000 times. That is how we describe RPM. But there is another factor, that is relative centrifugal force, that is RCF. Now, because when the particle is running in a centrifuge, it is acted upon by centrifugal force. True. But at the same time, gravitational force is still acting on it, right? So in correlation with gravity, when you talk about the effect of centrifugal field, it is described as relative centrifugal force, that is you are comparing with gravity. So that is described with letter small g, that we have to understand. So when we are talking about the process of centrifugation, the centrifugal force is used, that is going to help to sediment the particles or suspended materials from the mixture. You have diverse components, different components in a given sample, and the particles will be settling as per their size, as per their density, at their own rate. They will be moving and settling down. But you have to keep certain factors which are going to be common to all the particles which are separating. What are those? The centrifugation machine, the centrifugal force, then the time at which you are going to run it, right? And the relative centrifugal field, that is gravity, that also is going to be common to all of them. So when we talk about centrifugation, the very first centrifugation technique that dates back to 1806, right? Of course, after that, till 60 years, industrial application of centrifugation technique was not that much popular. First continuous centrifuge. It was designed by the Swedish inventor D. Laval. This is one of the companies also in the honor of his name also you will find, which is there on the market. So 1878 he prepared a continuous centrifuge. So that has got lot of applications when it comes to industrial application of centrifuge. Then the speed of the centrifugation at that time was as least as 3000 rpm only. Further came electrically driven machines in 1910, and the acceleration of the centrifuge was much better, and you had high speed centrifuges. So you know the types of centrifuge: low speed, high speed, then ultra high speed. That is how you name them on the basis of the speed they attain. And then ultra centrifuges further categorized as analytical ultracentrifuge and reparative ultracentrifuge. That is what you have studied in earlier classes, right? So when it comes to speed of the centrifuge in 1923, Swedberg S capital, that is what we write when it comes to Swedberg units, and we represent the value. The units are demonstrated as S, 16S rRNA, for example, or 18S rRNA. S is that sedimentation coefficient in the honor of the scientist Swedberg, who had invented analytical ultracentrifuge, and it was operating at 10,000 rpm at that time. And what it is not just simple common centrifuge, but it is equipped with a window, observation window. So sample when it is under rotation, under centrifugation process, can you imagine centrifuge is working, the tubes are kept into that, centrifuge is running, particles are settling, but there is a window through which you can see the particle is settling, real time monitoring of the settling particle can be done. Of course, no need that you are going to put your eye onto it. You can attach the microscopes to that, you can attach certain analytical instruments like spectrophotometer to that, and monitor the particle settling in terms of their properties, right? So when it comes to spectrophotometer, so refractive indices, absorption of light, all these will be calculated. Amount of light absorbed, amount of light transmitted, which wavelength is absorbed maximum, all these data you can collect, and that will help you to know the details about the particles which are running and separating under centrifugation, that is analytical ultracentrifuge developed by Swedberg. We have to learn the design of that instrument as well. Okay, now when we talk about separation using centrifuges, it is not about only the particles which are suspended in a given aqueous or any liquid material you are talking about, but as you all know, you can fragment the subcellular components by centrifugation technique, and that is differential centrifugation, right? And it was developed in the year 1940. Of course, in 1943, gaseous diffusion process. Have you ever heard about it? So instead of the liquids, you are talking about gaseous diffusion process, which is going to be used for separation. But yes, industrial scale gas centrifugation also was developed, and it was developed during World War II for separation of uranium isotopes. You know, Hiroshima, Nagasaki, and the radioisotopes and their effects, and world wars, and etc. I'm not going to go into that part, but it is just to catch your attention ki how or what is the history of history of this centrifugation technique and the instrumentation related to that. 1953, density gradient centrifugation was developed. So not only for separation of the particle, not only for monitoring the particle using spectrophotometer and analytical ultracentrifuge having a window to observe, but here you are able to separate particles based on their density. So density gradients are prepared, and particles will separate on the basis of their sedimentation rate. So sedimentation on the basis of density gradient. So it is called as density gradient centrifugation, which was further refined by Brack et al. In 1950s, and they applied the concept of uh, uh, density gradient purification for purification of viruses, right? And then further came the advancement, that is zonal centrifuges. Now these are the terminologies: zonal centrifuge, then density gradient centrifuge, differential centrifuge, then centrifugal force. We have to learn all these things one after the other. Now let's talk about the centrifuge and its applications. When we are saying, for example, if I want to separate animal cells, it would be enough to run the centrifuge at 200 to 2000 G force. Now here you just remember this term, I'll come to it. G, we have talked about centrifugal force, relative centrifugal force, RCF and RPM. We have talked about it in the previous slide. We will repeat that. But these units are in terms of centrifugal field, that is G. When it comes to mitochondria, chloroplast, you need to go to 15,000 G. But when you have, say, ribosomes, you have to go up to 3 lakh G. That is how the speed calculation RPM into G, that is RCF, or that is centrifugal G force, that is required for separating particles based on their size and density. So if you talk about cell or cell components, this table tells you that yes, depending upon the size and density of the particle, you have to choose a centrifuge which is going to operate at different speeds. So that this is one as low speed centrifuge, high speed centrifuge, and ultra high speed centrifuge. All right. So this is, till this I think you have learned in earlier classes. Now when I talk about the G force, right, or relative centrifugal force, then what it is all about. See, when I say force, hmm, so let's talk about the facts. That is, G is equal to the force, relative centrifugal force denoted by letter G, omega square R upon G. Now, what is omega? It is angular velocity. R is the radius of the centrifuge, and G is the acceleration due to gravity. Can you just imagine the instrument that you are using in the laboratory, right? You have the rotors. In the rotors you have the sockets to keep the tubes, and the rotors are either having small size tube, or they can hold big size tube, but they are the tube gets aligned at a particular angle with reference to the central shaft. The central shaft is the central axis of the instrument, right? But when it goes to individual tube socket, and you keep the tube into that, this is from the central shaft, it is at a particular angle. So your particle is rotating in a particular angle. It is not straight or parallel to the central axis of the instrument, right? So the omega is the angular velocity. R is the radius of the centrifuge. So the centrifuge tube that you are holding or using, that is going to have its own diameter, right? And that diameter of the tube, half of that is R, that is the radius of the tube. That is important, and its distance from the central shaft also is important. And G is the acceleration due to gravity. That is how we talk about the first formula, that is omega square R upon G, small g, that is equal to capital G. Alright. Now, this formula can be further modified, like here in place of G, you can add capital F, and you can add small f equal to, so capital F equal to m omega square R. Can we rewrite this? What is the formula now? It is m omega square. So it is capital F equal to m ओमेगा के लिए मैं W लिख रही हूँ, प्लीज एक्सक्यूज मी फॉर दैट, सो दैट वी कैन सेव ऑन टाइम. Omega square R. All right. So now can you tell me what this is? Omega square R, right? What is F? What F stands for? What is M stands for, and what R stands for? Now in this, F is the intensity of centrifugal force. M is the effective mass of the sedimenting particle. M is mass of the particle. Omega square R is same. Omega angular velocity, and R is the radius of the centrifuge. So that is, what is radius when I say R? Distance of migrating particle from central axis of rotation. The radius म्हटलं की फक्त centrifuge tube का radius, you will think it is not like that. The distance from the shaft, central shaft, you have to take into consideration. So R is equal to distance of the migrating particle from the central axis of rotation. So the force on a sedimenting particle increases with the velocity of rotation, true, but at the same time, it is going to be proportional to all these. Mass of the particle is not going to change, right? But it is going, force is going to be dependent on what? Angular velocity, and R is the radius, distance. So as the distance of the particle from the central axis increases, the force acted upon the particle also is going to increase. So the force on a sedimenting particle increases with the velocity of the rotation, and also with the distance of the particle from the axis of rotation, that we denote with letter R. So when we talk about uh, uh, the force, so you can write this formula, or you can write this formula to describe centrifugal force. What is the variation? Here we are taken into consideration the value of G, and here you are talking in terms of mass, right? M omega square R. Now let's go to the next formula, that is RCF is equal to 1.118 into 10 raised to minus 3 into R into RPM square. That is how you are seeing the formula. What is this RCF? RCF stands for relative centrifugal field, right? What is the difference between the two? What is the relation between two? Here is the relation between two. G, RCF into small g. All right. Now, when I see this, let's look into the details, right? A unit of measurement of revolutions, right? The revolutions are going to generate the force. So the unit of a measure of revolution is revolution per minute, right? And this is further referred to as, when you talk about an appropriate metric, it is referred to as relative centrifugal field, RCF. And this is determined using the formula RCF equal to 1.118 into 10 raised to minus 3 into R into RPM square. Now, from where are these values coming? That is a concern, right? Now, when I say RCF, why is 11.8 there? Why is R there? And why you have RPM square? Right? If you remember, in the equation, we have written F is equal to omega square R. Force, centrifugal force is equal to angular velocity into R. Then we have written the formula G equal to omega square R upon small g. Now, what is that small g? Small g is nothing but it's a relation to the Earth's gravitational force. So, Earth's gravitational force, when we say that is represented in the numbers, that is 980, right? So, can you imagine this particular formula if I start writing as G equal to omega square R upon 980, right? Now, in place of omega, if I talk about a particle which is spherical and it is getting a centrifuge, then omega is equal to pi into RPM upon 30. So this is the relationship for a particle which is spherical. And then if you substitute these values, you get this particular formula. All right. So it is with reference to considering a particle under centrifugation is circular. So you bring into equation the symbol pi, then pi into RPM upon 30 is equal to omega. That is how you are going to rearrange the equation, and the RCF is equal to then omega square. So omega square is nothing but pi square RPM square upon 30 ka square, right? And this is divided by 980. So all this calculation, if you do, it will come to the value 1.118 into 10 raised to minus 3 into R into RPM square. So if you are considering the relationship, it is very clear that since all the values are constant, the RCF depends on RPM and radius of rotation, because this number is constant, right? So RPM is the speed at which you are running it, and R is the distance of the sedimenting particle from the central axis. So this is the equation when we talk about RCF, right? So just imagine a centrifuge and you have kept the tubes. Now is the tube going to move if your centrifuge is of fixed angle type? No, they are fixed in a particular angle, right? So what is going to happen is the R also that is experienced by the tube is at a particular position in fixed angle, is going to remain constant. So ultimately, RCF is going to be largely dependent on variations in RPM value alone, right? So in true terms, if you talk, R is the distance between the particle in the sample holder and rotor axis. Can you just draw the diagram, the central shaft, and from the central shaft, you just draw the outer margin that shows the rotor design and the tube into it, right? Schematically represented. Or you can just imagine the picture of the centrifugation process, right? So R is the distance of the particle in the sample holder and the rotor axis. Now, here this is my tube which is completely in a horizontal position. Yes, is it going to happen like that? This will happen if my centrifuge is working uh, uh, with not a fixed angle rotor but swinging bucket type of a rotor. So when the tubes are rotating, they will flang out and will get arranged at a horizontal angle, and then they will spin. This particular design shows spinning. Against this, if I have a fixed angle rotor, my tube will be held at a particular angle. We will talk about the specific designs in details. However, whatever you have used, I'm trying to make you recollect how is the rotor, how is it going to hold, how many tubes is it going to hold, and is the position of each tube in the rotor fixed? Yes, it is fixed, right? So R value also is fixed. So this is fixed, R is fixed. So RCF is going to be governed by revolutions per minute. So in two terms, R is the constant factor. The calculated factor also is constant, and RCF and RPM, they are related. The speed of a centrifuge rotor, when you are going to talk either in terms of RPM or you can talk as RCF. But different centrifuge, they have different designs. So they will have different radius, right? So this will give to variation in RPM and RCF. What I say, this is constant, fine. R also is constant. R also is constant, right? So only RPM will decide the RCF. But can you imagine that there are the rotors of different sizes? So distance from the shaft, right? So you can imagine a rotor of this type. So here is the distance. But if my rotor is having a tube which is placed here, and this is the distance, so is the R value changing? Yes, surely changing. So for uh, rotors having different R value, RPM cannot be same. So this is very important when you have to choose a particular rotor, right? Given the speed is same. Now, if I have two instruments, two centrifuges running at revolutions per minute, that is equal to 12,000 RPM, right? But the R of one instrument is same 4.8 centimeter, and R for another is 8.4 centimeter. Will the RCF be same? Surely not, right? So you should be able to recall this equation that tells you that R is going to be a contributing factor if you change the rotor, if you change the design of the centrifuge. So size of the rotor, the design of the rotor are going to contribute variation in RCF value, because R also is going to change. RPM सेम रखा मतलब सेम इफेक्ट आएगा, ऐसे नहीं है. RPM revolutions per minute will give you separation in 5 minutes by any of the instrument if R is same and the type of instrument is same. That is, whether it is swinging bucket or whether it is fixed angle rotor, accordingly variations will be there. And second point is the distance of the particle under separation, its distance from central shaft. वो कौन decide करेगा? It will be decided by the type of rotor. So it is very important. So if I tell you, just take your pen and paper. If I have rotor, centrifuge, right? Centrifuges are there and they are running at 12,000 RPM. Now, as I said earlier, one has radius 4.8 and another has radius 8.4. Calculate the RCF value. How will you calculate? 1.119 into 10 raised to minus 3 into 12,000 whole square, right? And multiplied by R. In one case it is 4.8, in another case it is 8. So can you find out RCF values? Just you have to solve this. Yes, if you solve this, you will get to know that the values for RCF will be differing. For one, it will come around 7,700 something, and for another, it will come around 12,800. So G values, RCF values will be differing. That you have to remember the relation between RPM and RCF. Yes, it is equal. RCF is equal to RPM provided you have these values constant. R is constant, R is same for both, right? Then you will get the similar outcome of the process, right? So to what we do is always we express the force acting upon particle in terms of RCF rather than RPM, because RPM doesn't tell you what is the radius of the centrifuge that you are using, and it is very important factor. So if it is neglected, then your results will be affected. There will be ambiguity in the work. You won't get better separation. You will have to go for trial and error. So always you have to remember that you should talk about the type of rotor, type of centrifuge, and R, that is the distance from the shaft, is to be taken into calculations when you are going to talk about the efficiency of the instrument. RPM alone cannot tell you about which centrifuge is better. So I am having a centrifuge having 12,000 speed and another is 14,000 speed. But one is having R 4.8 and another having R 8.4. RCF will be different. And so effective separation will be taking less or more time depending on what is the R, right? So you have to choose appropriate centrifuge whose R and RPM are known, then you can predict about RCF generated, and then you can predict about the efficiency of or the time required for separation. You can compare for the two different centrifuges, right? So apart from RCF, rate of sedimentation of a given particle will also depend on certain more characteristics of the instrument, which include of the instrument and more than that, that of the particle itself. Right. So, what are these particles? Which are what are these factors which affect the movement of the particle when it is settling? One is terminal settling velocity. D is the diameter of the particle, assuming that the particle is spherical shape. Rho is the density of the solid particle, right? And of course, density of the suspending media also is going to be very important. That is uh, rho alone. Here rho s for particle and rho alone is for liquid in which the particle is. And another important factor is viscosity. More the viscosity, more is the resistance. Alright. So viscosity of the suspending fluid also is very important. So the factors which contribute to sedimentation are not only centrifugal field and the R value, that is the distance of the sedimenting particle from the shaft, but the terminal settling velocity, then D, the diameter of the particle, then the density of the particle, that is rho s, density of the suspending media, that is denoted by letter rho, and viscosity of the suspending liquid, that is the fluid in which your particle is. All these are going to be very important, and the relationship between them can be seen in this particular equation where VW, that is the terminal settling velocity, is given by d square upon 18 mu into rho s, that is density of the particle, minus rho of the rho, that means density of the suspending fluid, omega square r. So G equal to omega square r or F equal to m omega square r. These equations, they get rearranged when it comes to finding out settling velocity of a particle. Based on the properties of the particle, you can calculate settling velocity, right? Here is another thing, the time required that you can calculate, right? What are the things you can calculate? The speed, RPM. What you can calculate? RCF. What more can you calculate? G value. What more you can calculate? F value. What more you can calculate? Terminal velocity of sedimenting particle. And ultimately what you need is how long to run the centrifuge. The T is to be calculated, right? So the equation gets rearranged in this manner when you are calculating the time required. So G is equal to omega square R upon small g. That formula you remember we had seen in this particular slide. Now this G you are substituting in this equation over here. Rho minus rho 0. Now here again rho s and rho, These are the two things which are not changed, only the way the symbols used are changed. Rho 0 is that of the solvent, and rho is that of the dispersion, that is how densities they have referred. And d square is the average diameter of dispersion, that is particular cell or whatever it is, right? Path length of suspension in a centrifuge tube, L, that is nothing but your R, the distance it is going to travel. So these things put together will help you to calculate the time required at which the centrifuge should run to give you good separation. So this is about the principle of centrifugation technique. Here are the different things, like this is fixed angle rotor, this is swinging bucket rotor, right? Here angle is fixed, right? You can imagine this is the shaft and this is the angle, but here it is completely horizontal, right? So these are the two basic designs of a centrifuge rotor, where you have a fixed angle rotor, and this is the position of a tube when it is placed in a swinging bucket rotor, right? So this was introduction and summarization of what you learned earlier. Now in next lecture we will talk about more details.